I'm Benjamin Pingault. I work at the Cavendish Laboratory as a final year of my PhD, and I'm working on quantum technologies, and more precisely on impurities in diamond for quantum computing. I'm shining lasers at pieces of diamond and actually addressing single impurities, which are atomic size, so pretty much single atoms, trapped in the diamond matrix. And those impurities then emit light back, and we analyze this light to deduce some quantum properties of those impurities. So once we've found the impurities, we try to evaluate whether its properties are suitable for what we want to do. And more precisely, we want to see if this impurity can retain a quantum information for long enough time for us to process it. So the idea is that it shouldn't be disturbed too much by its environment in the matrix, because we're talking to one atom which is surrounded by billions of atoms. So there's quite a lot of cross-talking, and we want to make sure that this cross-talking is minimum. So in current computers, information is stored and processed using computer bits. So the information is encoded as 0 or 1. But in the quantum world, things can be in what we call superposition of states. So things could be, for a quantum bit, 0 and 1 at the same time. And so if you imagine taking several of those systems at the same time, having this capacity of being in several states at the same time, you could store and process information in a much more efficient way. So quantum computing would be able to solve complex problems much more efficiently than classical ones. And for example, simulating complex chemical reactions, refining considerably weather forecast, or financial optimization, for example. Many problems which nowadays are very complex, but quantum computing could bring this capacity of solving certain elements much more efficiently. And it's not just about solving complex problems, it's also an issue for security, because the current encryption technology is based on factoring large numbers, but with a quantum computer, such factorization becomes much faster, and so suddenly this system is not secure anymore. So there are also issues of security with quantum computing. So as a physical implementation of a quantum bit, there are many options. Trapped atoms using lasers, directly trapping the individual atom, not in a solid-state matrix. There are some other systems, such as a system called quantum dots, which are based on semiconductor technology. You can have even some impurity atoms in silicon. So there are many options for implementing a quantum bit. And diamond, impurities in diamond are just one of them. And each of those possibilities has its advantages and its drawbacks. Trapped atoms are very nice. They can store information for a very long time, but they're very difficult to scale up. You can trap a few atoms, much progress is being made, but it's still very difficult to scale up. Whereas if you've got a piece of diamond, all your atoms, all your impurities are already trapped into this matrix, and you don't need the complex laser trapping mechanisms that trapped atoms need. For other solid-state systems, most of the time the difficulty is that there's, as I mentioned, lots of crosstalk with the environment, and so it's difficult to optimize the time during which they can hold this quantum information. And so that's what we're focusing on quite often.